This problem is very much like our gelatin problem that we did before, right? Because the bullet gets fired through the block, right? And it exits the block. So we have so the bullet retains some momentum, right, of its own, which means the block will have its own momentum. So it's not a what? It's not a sticky, it's not elastic because it doesn't bounce, but it's not a sticky collision either. Okay, what do we call, what's a sticky collision? And what do we call it? What's that called?
Inelastic.
Perfectly inelastic. Sticky. Okay, elastic means that they bounce and energy is conserved. Okay, so do you expect potential energy to be conserved here? No, so it's not elastic, and they don't stick together, so it's not perfectly inelastic. It's just an inelastic collision of somewhere along that continuum. All right, so we have a surface here. We're going to put a block on it. All right, and then a bullet that's going to pass through it. So here's our initial condition, and we have some initial velocity, and we have mass here, and we got m here, right? So this is at rest, right? So v for the block, v is equal to 0, v for the block, okay? So now we use, remember we use v's and we use u's. We use u's. All right, so now we know that afterwards we'll do exactly the same thing. Take all of this, not that, this. All right, I'll get that back, don't worry. All right, now we're going to pull this down here, and now after the fact, the bullet's over here, and it's not v naught, it's u. In fact, we'll just call it u, and we still have mass m. All right, and now this velocity of the block, now it's u for the block, is not equal to 0, and we got to figure out what it is. Okay, so I'll put a red dashed line in there representing the event or the incident. All right, so now what do we know? We know that the total momentum here, up at the top, has got to be equal to the total momentum down here at the bottom. At the top, all the momentum's wrapped up in the bullet. The block has none. At the end, the bullet has less momentum, right? So the block must have increased its momentum. It will also be positive. All right, remember that momentum is a vector, so direction does matter, unlike in energy, where it doesn't matter because it's a scalar. So what we end up with is m bullet. I hate b's for bullets and blocks, but it always works out that way. M little b for the little bullet, all right? M v naught plus 0, right, because the initial momentum of the block is 0, is equal to m little b u little b, plus big M, which is mass of the big block. We could have left off that little b, times u for the block. All right? We're solving for u for the block. All right? So now all I have to do is a little bit of algebra voodoo. So we're going to say u for the block is equal to mb v naught minus mb ub all over big M. Yep. So now we have ub, we have final velocity for the big block is equal to the mass of the bullet, which was teeny. Oh, that's right. I threw it off here. Mass for the bullet was 0.150 kilograms. 0.150 kilograms times v naught, which was 715 meters per second. Wow. 715 meters per second minus, well, actually, we could just group that, can't we? That's right, I'll just do it this way. Should have done this to start with, 0.150 kilograms times its final velocity, which is, anybody remember? 40 meters per second. Okay, so 40 meters per second. All divided by the mass of the block, and I still don't remember what it was. I think it's 2 kilograms. Yeesh, gonna get dizzy here. It is 2 kilograms. So we're gonna have kilogram meters per second, gotta divide by kilograms meters per second. So then we get, so UB is equal to 0.150 times 715 minus 40 all over 2. And dimensionally, we know we're going to get meters per second. And so we get 0.150 times, you go to calculator?
Yeah,
50.625. 50.625. Final velocity of the block. Thank you.